Okay, in this series of lectures, we're going to be looking at how motion and force relate to one another. We've talked a little bit about motion, we've talked a little bit about force, now we want to see how they connect together. And we're going to do that through Newton's laws of motion. In particular, Newton's first law, his second law, and his third law of motion. And these laws all are about how forces and interactions interplay with motion. And so we're going to summarize Newton's three laws, and we're going to focus on understanding what they mean and what they tell us and how we can use them to understand our world and figure things out about it. So let's look at Newton's first law of motion, which is also called the law of inertia. It says, every object continues in a state of rest or uniform speed, that means constant speed, in a straight line unless acted on by a non-zero force. And so again, you have to have a net force. If I've got some sort of block here and I apply a force from that side and a force from that side, if one of those forces is bigger than the other, there'll be a net force. And the excess force will win and the block will slide either to the left or the right, depending on which force is bigger. But if these two forces are the same, there's no net force and there will be no motion of this block. Now, this is called the law of inertia. And basically, there's another way to think about it. The law of inertia tells us that an object wants to keep whatever state of motion it has. If it's already at rest, it wants to stay at rest. If it's already in motion, it wants to keep that motion, and it will only change that motion if you apply a force to it. It will only change being at rest if you apply a force to it. So I like to give a different formulation of Newton's first law. I like to say it this way. Okay, we can say to accelerate an object, one must apply a net force. That is a non-zero excess force. To accelerate an object, one must apply a force. What do we mean by accelerate? Remember, when we say accelerate, we mean speed up, slow down, or turn. So if something is sitting on the table at rest, it's only going to speed up if we apply a force. If something is sliding across the floor, it's only going to slow down if we apply a force. If something's moving in a straight line, it's only going to turn if we apply a force. And so to accelerate something, to speed it up, to slow it down, or to turn it, to accelerate an object, one must apply a net force. That's Newton's first law of motion. Now, another way that you can say that is that objects resist a change in their state of motion. They want to keep the motion they have, whether they're sitting still, whether they're moving in a straight line, whatever motion they have, they want to keep that motion. So you have to apply a force to change the motion. Things resist changing their motion. And that property, the property of matter in our universe, that it resists a change in its motion, is called inertia. That's why this is sometimes called the law of inertia, because inertia is a property that things have. They resist a change in their state of motion, or they resist being accelerated. And so if you have a tablecloth sitting on a table and you've got a candelabra and you've got a goblet and a plate and there's some food on it, and if you slowly pull the tablecloth off, you'll drag all these things with it because you are letting the friction pull on these things. But if you jerk the tablecloth off really fast, and you guys probably have seen magicians do this kind of a trick or seen it in movies, if you jerk the tablecloth off, these objects all have inertia. They all resist being accelerated. And the tablecloth gets pulled out from underneath them because the friction isn't acting in a way that's able to pull them off with it. That's because these things have inertia. They want to stay where they are. They don't want to move along with the tablecloth. And again, that property is called inertia. So there's quite a lot to unpack on this slide. If you need to, pause the video, write things down, think about them, and of course, if you have any questions, let me know. I'll be happy to answer them. So let's see if we understand this. Here's a quick little multiple choice deal to test our knowledge. It says a sheet of paper is quickly withdrawn from under a soft drink can without the can toppling. How does that happen? So I've got, this can here. It's a Mountain Dew or whatever. and there's a sheet of paper underneath it, and if I grab the paper and I pull it with a force, if I pull it, that can is just going to sit there, just like the stuff on the table before. What is that that allows it to do that? And so our options are that the gravity is pulling harder on the can than the paper, that the can has weight, that the can has inertia, or none of the above. So gravity pulls on the can harder than the paper. Well, I think if you've had a can of Mountain Dew, you know that it probably weighs more than a piece of paper, so that's probably not the right answer. The can has weight. It is true that the can has weight, but that's not why it doesn't topple. The can has inertia. I think you know that's the right answer. That the can doesn't want to be moving to this left in the direction of this force. And so what's going on? I pull on the paper. The paper transmits that force to the can through friction. But if the paper is jerked too quickly, the friction will not be able to drag the can with it, and the can will just sit where it is. That is the law of inertia. So I think we can say that the answer is the can has inertia. That is the right answer. Okay, here's another idea of understanding this concept of inertia. And so the example here is if you swing a stone overhead in a horizontal circle and then the string breaks, which way is the stone going to move after the string breaks? Okay, here I've drawn my stone and my string, and it's being swung in a horizontal circle here. I'm kind of looking at it top down, and so this stone is being swung back and forth, and at some point the string breaks, and so there's a cut in the string. And so at the moment the string breaks, what's going to happen to the stone? Which direction is it going to go? Is it going to keep following the circle, the curved path? Is it going to move in a straight line? Is it going to move in some kind of spiral path? Which way is it going to go? Is it going to go in some sort of vertical path? That would mean literally the stone is coming out of the screen towards your face as you're watching this video. That would be like a vertical motion since this is a horizontal circle. Probably it's not going to do that. But what is it going to do? And so the thing you have to recognize is that what Newton's first law says is that things want to move in straight lines or they want to stay at rest. They don't want to move, they don't want to change their direction, they don't want to slow down or speed up. They want to keep the direction they have unless you apply a force. So if this guy is moving in a circle, how is it able to move in the circle? Because there's a tension in this string. You have to be pulling the string back to keep this guy going in a circle. Once that string is cut, there's no more force keeping this guy moving in a circle. And so remember, things will either stay where they are or they will move in a straight line. They will not change their direction unless you apply a force. And so once the force goes away, the motion of the stone will be in a straight line. And so that is the answer to our question, is going to go in a straight line path. So here are some more examples of this concept of inertia. We have a coin that's sitting on a piece of cardboard that is resting on a cup. And this is a sort of a classic demonstration that if you thump the piece of paper and knock it off, the coin will fall straight down into the cup. And so the reason for that is the same idea. The coin has inertia. The coin wants to stay where it is. And so you thump the piece of cardboard, it flicks off, but the coin stays where it is, and then once the cardboard is no longer supporting it, gravity is going to pull it straight down into the cup. So that's the basic idea. So here's another question. Why do the downward motion and sudden stop of a hammer handle tighten the hammer head? So if you've got a hammer that's loose on the hammer handle, if the head is loose on the handle, if you take it and slam the butt against the floor or against the tabletop, well, the entire hammer, including the head, is moving down, and then all of a sudden the hammer hits the tabletop and the wooden part stops, but that head, it was already moving straight down, so it wants to keep moving straight down. So basically it hammers itself down onto the handle harder, and that will tighten it up. And then here is the third example of inertia. We have this string which is attached to this mass, and so there's a string here that we're pulling on, and another string which is fixed to the ceiling. And so you can actually break either string depending on how you pull. If you break with a fast jerk or a slow pull, the strings will break differently. A sudden downward yank will break the bottom string. A slow pull tends to break the top string. So why is that? Well, this guy has inertia. It wants to stay where it is. And so if I jerk down, that inertia is pulling back on this bottom string, and it's going to be where the weakness is, and it's going to break. But if I pull slowly, that force can be transferred to that top string, and so you're slowly pulling this down. And so that's why the top string is going to tend to break. It all has to do with this guy having inertia, and it doesn't want to move, and you have to apply a force to it to get it to move. Here's another example. Inertia in action. If you've ever slammed on the brakes of your car, you felt yourself being thrown forward. If you've ever slammed on the accelerator of your car, you've probably felt yourself as if you were being thrown backwards. In both cases, that's because you have inertia. Your body wants to stay where it is. It wants to keep the motion that it has. And if that's sitting still, or if that's moving at a certain speed, your body wants to keep that state of motion. So in the case of slamming on your brakes, the car and you are both together moving at a good amount of speed. You say, oh no, I'm going to fall off the cliff here, so you slam on the brakes. Well, the brakes slow the car down. They act with the car, but you are still moving forward with the same speed that you had. And so you feel yourself moving forward. Now, if the friction between the seat of your car and your bottom is strong enough to slow you down with the car, you will not be injured by this. You may feel the force pulling you forward, but you won't actually slide in your seat. But if you have like a massive acceleration so that the friction cannot maintain you in your position, you'll actually go forward and slam into your steering wheel. That's why we have airbags in cars, because if you are in an accident, you'll slam into the airbag, which cushions you rather than the hard steering column. And we can actually look at this another way. If we imagine ourselves in a car or in a truck maybe, and that truck starts accelerating that way. So it's at rest, you're just standing there, maybe you're in a bus, the bus driver hits the gas, and so the bus starts going that way. You feel yourself being pulled back. It's almost as if you want to fall backwards. But what's really happening is the bus is accelerating out from underneath your feet, and you're staying where you are. And so it feels like you're being jerked backwards, but really the bus is sliding out from underneath you. And again, you're wanting to maintain the state that you have. So if you and the bus together are standing there, then the bus accelerates. The friction in the floor has to accelerate you with the bus. And if it happens too quickly, you feel yourself slipping backwards. Here's another example of how inertia can work. So if you're on an airplane and the airplane's moving at a constant speed, and you toss a coin, that coin will go up and come back down, just like if you were standing still on the ground. Because if you're moving at a constant speed, there's no acceleration, and that means there's no need for a force. In other words, the state of motion of the coin is to keep up with you, because when the coin is in your hand, you and the coin are moving together with the plane. When the coin leaves your hand, you all have the same connection with inertia. You all want to maintain your speed, so that will basically mean that the coin will not deflect. Now, if the pilot hits the gas and the plane accelerates, then the coin will change its trajectory. But if the plane is moving at a constant speed, no force is necessary to affect the motion of that coin. Let's apply this idea another way. So the Earth is moving at about 30 kilometers every second. It's spinning on its axis. And so here's the idea. If the bird just drops straight down and the Earth is spinning this way, then you might think that the snake that the bird wants to catch, or the worm, or whatever it is, I guess it's a worm, sorry. Anyway, the worm, you would think that the worm would get away from it because the bird would go straight down, but the earth is carrying the worm away with it. But the worm, the tree, the bird, they're all moving together. They're all moving at that 30 kilometers per second. And so even though the bird drops off the tree branch and is falling down, he's got his inertia, which is going to keep him moving with the earth at that same speed. And so, yes, in a particular moment, the worm will have moved from there, but so will the bird. And as the bird falls, it'll actually catch the worm. Because if you were on the ground looking, it would look as though the bird just fell straight down. Even though the earth is moving and the bird is actually falling on a curved trajectory because of that, to someone standing on the earth watching them, it would seem that the bird goes straight down. And that's because the bird, the worm, the tree all have inertia. The next thing we want to look at is Newton's second law of motion. I think we've covered the first law, the law of inertia, pretty completely. Now, the first law says if you want to accelerate an object, change its motion, you have to apply a force. The second law of Newton tells us that the amount of acceleration you get. And so the acceleration produced by a net force on an object is directly proportional to the net force. It is in the same direction as the net force, and it is inversely proportional to the mass of the object. And so we have this little picture over here on the right. So we have a force applying to a brick, and if I take two hands and I double the amount of force acting on my brick, I get twice as much acceleration. That's what it means when we say that the net force on an object, or rather the acceleration produced by a net force on an object, is directly proportional to that net force. And so if I apply a force, I get a certain acceleration. I double the force, I get double the acceleration. If I increase the force 10 times, I get 10 times acceleration. Now it also says that the acceleration is inversely proportional to the mass. In other words, if I take my hand and I apply it to two bricks, I get half the acceleration. If I take two hands and apply it to two bricks, I get the same acceleration as one hand on one brick, because the bigger the mass, the smaller the acceleration. And we can actually write that as an equation. We can say that acceleration is equal to force divided by mass. And we can write that as a simpler equation. We can say that the A, acceleration, is equal to the force F divided by the mass M. And so I can simply plug in numbers for force and mass, and that gives me the acceleration. So let's look at this equation. We have the acceleration is equal to the force divided by the mass, or A is equal to F over M. So what happens if you have a small force and a large mass? So F is small and M is large. So you've got a small number and you're dividing by a big number, like 10 divided by 100. Well, that would mean that A would be very small. You've got a small number divided by a big number. Your A is small. That means your acceleration is going to be small. And the other option is that the force is really big, but the mass is very small. And so that would mean that you have a big force and you're dividing by a tiny number, which means that you're not dividing by as much, and your acceleration is going to be very big. And so that's going to give you a large acceleration. So let's look at an example here. Consider a cart which is being pushed along a track with a certain amount of force. If the force remains the same while the mass of the cart decreases to half, then what's going to happen to the acceleration? So this is actually a little bit tricky. So the acceleration is equal to force divided by mass, and the mass transforms into half the mass. So you've got this going on, and just half the mass just falls off. And so what's going to happen to the remaining mass after half the mass just falls off? So the force is remaining the same, but the mass goes to 1/2 mass. So there's going to be some new acceleration. So the new acceleration is going to be the force that we had, this is the unchanged force, divided by half the mass. And F over m, this F over m, that's the old A. So that's going to be equal to 1 over 1/2, because what we have here, we have got a 1 over 1/2 and then an F over m, but F over m is our old acceleration, and I can actually call that old up above. And so what is 1 divided by 1/2? Well, that's just 2. If we do 1 over 1 divided by 1 over 2, that's equal to 1 over 1 times 2 over 1, and that gives us 2. So our new acceleration is equal to twice our old acceleration. A new equals to twice A old. And so what happens is that the answer is that the acceleration of the cart is going to double. Now, this is a little bit tricky if you're a little sketchy on using your fractions, so look at this, make sure this example makes sense, and if you're confused by anything, again, let me know. I'll be happy to sit down with you and go over it. The next thing we want to look at is applying Newton's second law of motion to the case when an object is in free fall. So remember that the term free fall is something of a misnomer. In other words, that's a word that's a little bit confusing because it has the word fall built into it. But actually, something thrown up while it's going up is in free fall. And of course, it will stop momentarily at the top and then it'll come back down. And again, it'll be in free fall that whole pass. So what the word free fall really means is that only gravity is acting on the object. We're going to ignore air resistance and other effects. So if I throw something up, when it leaves my hand, from the moment it leaves my hand, only gravity is acting on it. So it's going upwards, gravity is slowing it down. Gravity stops it at the top, and then gravity accelerates it and makes it go faster as it returns. But all through that motion, the only force acting on it is gravity, and we say that that object is in free fall. So what does that mean? Well, when the only force acting is gravity, it's going to have a constant acceleration, and that constant acceleration is little g. And that value for little g is 9.8 meters per second squared. So 9.8 meters per second squared. That's the amount that little g is. Now, if we round 9.8 up to about 10, we can say that for quick and dirty calculations, we can say that objects near the surface of the Earth will increase their speed by 10 meters per second every second. So the acceleration is about 10 meters per second every second, or 10 meters per second squared. And so we want to see how that relates to the force of gravity. But before we do that, let's check and make sure that our understanding that this constant acceleration, let's make sure we know exactly what that means. So here is an example. At one instant, an object is in free fall, and it has a speed of 40 meters per second. So it's going to be falling straight down at 40 meters per second. Its speed 1 second later is going to be what? 50 meters per second. How do I know that? Because the acceleration is about 10 meters per second every second. And so if it's going 40 and it's falling downward, 1 second later it'll be going 50 meters per second. A second after that it'll be going 60 meters per second. Now here's a little tricky thing. What if it was going upwards at 40 meters per second? What would its speed be 1 second later there? That way, it would actually decrease. The speed would slow down by 10 meters per second, and it would be 30. So you have to know which way the thing's going. And in general, even though it's true that an object is in free fall when it's going up or it's going down, usually you can assume, unless you're explicitly stated, you can assume that it's falling downwards. Now, I want to talk a little bit about a guy named Aristotle, because he was this famous guy, and he wrote a lot about physics, but a lot about what he wrote ended up being wrong. At least a lot of what he wrote about physics ended up being wrong. And one of the things that he said was that if you drop 2 bowling balls Obviously, he didn't have bowling in ancient Greece, but we'll just say if we have two bowling balls, but they're the same size, but one of them is much heavier than the other. According to Aristotle, if you drop them both at the same time from the same height, you would expect the heavier ball to hit the ground first. And his logic was gravity's pulling down harder on the heavier ball, so it's going to hit the ground first. But if you actually apply the scientific method and you do an experiment, in other words, you test your hypothesis, it's very easy to determine that Aristotle was in fact quite wrong. If I drop two balls that are the same size, from the same height, at the same time, regardless of whether they weigh the same or they have different weights, they're all going to have the same acceleration. What is that acceleration? What will the acceleration be? That acceleration will be little g, which we know is about 10 meters per second squared. And so why is it if one of them is heavier, if this is the heavier one, so let's say this one is heavier and this one is lighter, why doesn't the heavier one fall faster? Because gravity is pulling down on it harder. That's the question, right? So let's look over here at our figure on the right. We've got two examples. We've got a block with some mass m, and then we've got two of those blocks tied together, so total they have double the mass. And so we can apply the acceleration is going to be the force divided by the mass. So in this case, we have one block with a mass little m, and we have one force representing the force of gravity. And we know that for that mass, that acceleration is going to be equal to little g, 9.8, or actually we'll say close to 10. Now, if I double the mass, I now am dividing by twice as much mass, but I'm also got gravity acting twice as hard because it's twice as heavy. And so if I calculate the acceleration, the total force divided by the total mass, I still get these twos will cancel. I get F over m, which is still equal to g. So the key idea here is this. Yes, gravity is pulling harder on the bigger mass, but the bigger mass also has a bigger resistance to being accelerated. It has a bigger inertia. And so the bigger force acting on the bigger inertia cancels, and you're left with the same acceleration. And so no matter how much mass you have, if you can ignore wind resistance, you're going to get the same acceleration for every object you drop. And it doesn't even have to be the same size. Any object dropped near the surface of the Earth is going to accelerate at that rate. Now, there is one exception to that, because implicit in all of these discussions is we're pretending that air resistance doesn't work. But in the real world, air resistance does work. And so things that have more area to catch the air, they may get more air resistance, or things that are very, very light, like a piece of styrofoam, may be buffeted by wind currents more than something like a bowling ball would. And so these things can affect how things fall down to the ground. But if you can ignore air resistance, and it turns out for most small objects dropped relatively close to the Earth, you pretty much can. So in those cases, we're going to ignore air resistance, and we see that the principle works. So here's an example. A 5 kilogram iron ball and a 10 kilogram iron ball are dropped from rest. And the question is, if we can ignore air resistance, if air resistance is negligible, what's the acceleration of the heavier ball compared to the lighter ball? The acceleration of the heavier ball, will it be less, the same, more, or is it impossible to know? Well, obviously it's impossible to know. I'm just kidding. No, of course it's possible to know. We just figured out that it's going to be the same. So the answer is that it's going to be the same. What is it going to be? Little g, or about 10 meters per second squared. Now let's ask a different question. We have our same 5 kilogram ball and our same 10 kilogram ball, and they're both dropped from rest. When the free-falling 5 kilogram ball reaches a speed of 10 meters per second, what will the free-falling 10 kilogram ball be? What will its speed be? Less than 10, 10, more than 10, or impossible to know, undetermined. So what's the rule? How do things accelerate? Everything accelerates at the same rate, little g, 9.8 or 10, or about 10 meters per second squared. So if the first one is moving 10 meters per second, the second one is going to have accelerated the same amount. And so it will also be moving about 10 meters per second. And so that will be our answer. Now there's a famous physics experiment. You have a glass tube that's enclosed, and inside you put a coin and a feather. And then you flip it upside down so that they can both fall. So, you let this fall to the bottom, then you flip it up, rotate it 180 degrees, and so when the coin and the feather get to the top, they're both going to fall downwards. And the question is, which one's going to hit the ground first? And so it turns out if you do this experiment, the coin hits the bottom first. Wait a minute. How is that possible? We just said that everything falls at the same rate. Oh, but we didn't say that, did we? We said everything falls at the same rate if you can ignore air resistance. A feather is very, very light, and it has a lot of surface area compared to its weight. A coin is very, very dense. And so what happens is the air resistance is really much stronger on the feather than it is on the coin, or it has a bigger impact on the feather. Maybe that would be the better way to say it. So the impact of the air resistance on the feather is much stronger than the impact of the air resistance on the motion of the coin. So that's why the coin is able to hit the ground first. But if you repeat the same experiment and you hook up a vacuum hose and you suck out all the air so there's no resistance, no air resistance possible, and then you repeat the same experiment, what happens is the coin and the feather will hit the bottom at the same time every time. And that is inertia in action.